Okay, so probably the more important aspect of network management when we look at the kind of traffic that we put onto networks. We're going to look at multicast. So multicast IP addressing is something that's quite difficult for people to understand. So we have this concept in multicast of a multicast group, and in IPv4 we have what we call a destination multicast IP address. So this is a special IP address which I send to, and it doesn't relate to a IP stack in a host. It's just an address that sits out on the network. So this is one of the first complications with IPv4. So when we do traditional networking lessons about unicast, everybody says it's very important to make sure that your device has an IP address in the same IP subnet as the sending device. That means I can send from a source IP address to a destination IP address, no problem. Multicast IP addresses go to a special range which are in their own IP subnet, which means that I have to open up what we call a listener on my normal IP device into that different IP subnet. So I begin to kind of bend the rules of what people would tell you about doing IP subnetting. And this is what makes multicasting fairly complicated to understand, because we're dealing with special IP addresses which don't look like they should be able to get to your device. Well, strictly they shouldn't. So, for example, my computer here may have an IP address that could be 192.168.1.10, quite a normal one, but I could tell it to listen to a multicast IP address at 239.255.100.102. Now that is in a completely different IP subnet to the IP subnet I have told you that my laptop is in. So how can I actually have communication with that special IP address? Well, it's a software trick. The people who wrote the operating system, in this case Windows, have to write a special piece of software to go, okay, you can listen in your own IP subnet, but shh, there's this special IP subnet over here that you can also listen to. So it doesn't exactly follow the rules as you would get in the first instance. So it becomes slightly confusing. Furthermore, an IP multicast address is actually a destination that has no physical entity. I attach to that destination from the other end, so I'm creating a connection of a bridge like that rather than a single point-to-point link. Now, in order for this to work, we have to have special IP addresses that are reserved for this purpose, and also we have to have special MAC addresses. Because switches understand MAC addresses, we have to have special reserved MAC addresses to tell the switch that this is multicast traffic. So when I send a multicast message to a switch, it goes, aha, I know what that MAC address is. I need to send that traffic out of every port on the switch, which is what happens with unmanaged multicast. Not a problem, because my special multicast IP address range is 224.0.0.0 up to 239.255.255.255. Now, anybody who is really into very fast mathematics will see a slight problem with this. So we say that our MAC address range starts with 01005E for multicast. Now, a MAC address is 48 bits long, so that means it's 6 pairs. I've used up 3 pairs describing it, so I only have 24 bits left to describe my individual multicast MAC addresses. if I look at the range of IPv4 multicast addresses, I can see that that's actually a lot bigger than 24 bits. So I have a problem. Multicast in IPv4 is quite broken because I can have up to 32 multicast IP addresses for every multicast MAC address, which is a problem. If I have a video stream, say I have a camera and I'm sending double frame rate 4K pictures, that is 12 gigabits per second. And I can send that on a multicast IP address. I can send another stream of video on the next IP address. But when I look at which MAC address they're being sent to the same MAC address. If I allow that same MAC address just to go through a switch, I could create all kinds of chaos with the amount of traffic. So I have to do something inside the switch to look at the multicast IP addresses and compare them with the multicast MAC addresses being used. Now, if in 1996, when the IEEE were asked to assign an individual MAC address for every single multicast IP address, they had actually done this, multicast on a switch would be really easy, because all the switch would do would be just map a single IP address to a single MAC address and just go straight through the routing table like normal. But they didn't, unfortunately. So we need to use something called IGMP snooping to solve this problem, which is quite processor intensive. So IGMP is a protocol used to manage multicast inside IPv4 networks. In IPv6, it gets replaced with MLD, which is multicast listener discovery. It's a much more efficient mechanism. And what this does is it helps to manage multicast traffic getting everywhere in the network. Now, without this technique, multicast traffic gets forwarded through every single interface in the network, and from a bandwidth perspective, it uses bandwidth like broadcast traffic. And that's a bad thing because you end up wasting bandwidth. So IGMP helps to work out which devices want to listen to which bits of multicast and make sure that they're only delivered the multicast traffic that they ask for. And how we do this, we send out query messages from the multicast router, and the devices that are interested in the multicast traffic send reports back to the querier saying, I want this particular piece of multicast. And the switches in between the querier and the device asking for that traffic listen out for those requests and set up forwarding tables accordingly. All Dante devices do implement IGMP as a host, so they can ask for specific pieces of multicast. So the key things we need in order to make IGMP work are an IGMP querier. Now, the nice thing with this is that most modern switches today which support IGMP are able to function as an IGMP querier. And what happens is a query message is periodically sent to this special multicast IP address, 224.0.0.1, which is called the all hosts multicast IP address. That means all the switches will forward this automatically without having to be told to. And it basically says which group addresses do you want. And when they receive this message, the host will send back either on 224.0.0.2 or 224.0.0.22 a list of which specific multicast groups they want to listen to. Now, this is a key thing. You should only have one active querier in each broadcast domain. If you have multiple queriers, everybody gets confused because it's like having two bosses asking for two different things, but two very similar things, but not exactly the same. And I'm sure we've all worked in situations like that. It gets very, very frustrating, and computers really don't like it very much. So just be careful about that. It is possible to configure multiple queriers with some clever equipment, but it's not a standard thing to do. So our best advice is to avoid having that situation. Now the switches in between listen out for that traffic. They listen out for the queries, which mention the different groups, and they listen for the reports. And they basically set up rules in their forwarding tables to go, okay, this particular multicast traffic can go on this port to this device, but not on this port. So it's much easier to visualize this. So we have a switch here, and we turn on IGMP snooping, which immediately stops any multicast leaving the switch. In order for us to actually deal with multicast now, we need to turn on the IGMP querier, and the querier will send these kind of messages. So it will send a general query, and that will go to this all host address and come out of every single switch port. And the devices will send back what we call a general report listing the IP multicast groups that they are interested in. And then the switch with IGMP snooping will see these messages and allow those particular multicast groups to go to these devices. And you see the device here that doesn't want any multicast. The switch stops forwarding any multicast, and same for this guy. It doesn't send any multicast because he doesn't want any. And this switch only receives the multicast it has asked for. And this one wants 3 different groups, so it will get those 3 groups. And this message helps the switch to populate its snooping table, which lists which multicast groups go to which switch ports. So that happens every 30, 45 seconds or so that the switches can stay up to date with which multicast traffic everybody wants. Now there's another kind of IGMP query that is a group-specific query. So if I suddenly set up a new multicast channel, so for example I set up a new flow in Dante with new multicast, this group-specific query will be issued from the querier, basically saying, giving the group address, here 239.255.255.33, and that will be who wants this? And then the device will simply reply, I do, and that will help populate the forwarding table quickly. So there's one other kind of message that has been missed out on this. We've missed out the circumstance where what happens if I was listening to a multicast group and say I'd taken my box away and I had plugged it in somewhere else. Do I have to wait for the querier to come round and go, who wants this multicast group again? Well, no, that would be silly because we have to wait a long time potentially for that to happen. So there is a third kind of report that comes from a device. If it was already listening to multicast, it will send something called an unsolicited report. And what that means goes, hi, yeah, I was listening to this multicast earlier, I want it again now, please. So it will create an immediate connection rather than having to wait. And we do that with Dante devices all the time. So to make IGMP version 4 work more smoothly, we have specific roles within the network. We have the querier, and inside the querier we have timers. So we have query intervals, and we have timeouts, and we have other time-specific functions. We also have specific multicast addresses. So 224.0.0.1 is a very important multicast IP address. So are 224.0.0.2 and 22. There's also multiple versions of IGMP, so there's version 2, version 3, etc. And the protocol implementations are different on different switch vendors. So be very careful about mixing different switch vendors' implementations in the same network. It can be unpredictable. And there are certain optimizations vendors do, like a fast leave or query of proxies, which are in addition to the standards and can help and can hinder. So simple rules, the normal rules of network configuration. If you start randomly changing things, random effects will occur. So generally only change one variable at a time, otherwise it's very, very difficult to troubleshoot. Okay, the temptation is to try and change lots of different things because you make assumptions, and with networking, altering more than one variable is the key to actually making a mess. So one variable at a time, no matter how tempting it is to change multiple things at once. So here's a simple recipe. Quite a lot of the time people say, well, what about this, what about that? Well, the chances are, if you've done some reading on the specific implementation you have, you're probably right. This is just meant for people who have never touched IGMP before to get started. This is as simple as it gets. So the first thing to do is make sure that you have a short query interval. So something like 15 or 30 seconds is absolutely fine. Now what this does is it minimizes your potential for gaps in audio. This means the query goes out more often, the network forwarding tables are kept fresher, so it means that any change in the network is responded to more quickly. Leave the timeout value as the default setting. Normally the longer timeout value that you have is the better, because it means that you can miss some queries and the audio stays working. This may not be great advice if you're using a video system, because you want video system bandwidth to clear very, very quickly, because it's very big. Audio, as I said, is very small, so 6 megabits per second for 4 audio channels is nothing. You can leave 6 megabits per second hanging around in a network for a short amount of time and it will not do much damage. 12 gigabits per second, probably a different story. So for audio, you can be more relaxed about these things. You want to keep the audio running and it's not a big cost in terms of overhead. Make sure there's only one active querier per VLAN at the same time. So ideally this is a switch near the middle of the network. What this means is that the distance between the querier and the endpoints is as small as possible on average. If you have multiple queries, you could get intermittent audio because the forwarding tables will refresh at different rates and with different information. To work this out, just put Wireshark onto the network and have a look for the IGMP query messages, the ones going to 224.0.0.1, and look for multiple sources. Are they coming from multiple source IP addresses? If they are, that means you have multiple queries that are running active. From our perspective, don't worry about using fast leave. It doesn't offer anything from a Dante perspective. Generally don't use IGMP proxies unless, of course, you've gone on a big course on how it specifically works in that switch platform, but I would generally avoid them. And watch out on certain Netgear switches. If you tick block unregistered multicast, unfortunately they think that MDNS is unregistered, which it isn't. It is definitely registered. And it also thinks that PTP is unregistered multicast traffic, and that is not true either. PTP is definitely registered traffic. So it's just a bit out of date, and it will cause all kinds of strange problems to occur in your network. Dante devices support IGMP version 3. The good news there is that there's no specific reason why we support version 3. It's just it was the newest one around when we wrote the IGMP implementation. One of the most boring things about networking are people making a big deal about version numbers when it really doesn't matter. Okay, our reason is we did version 3 because it was around at the time. It's more likely that if someone was going to get rid of a version of IGMP, it would be version 2 first, then version 3. But because version 3 is backwards compatible with version 2 anyway, it's unlikely they'll be got rid of. And we don't use any of the feature enhancements of version 3. So yeah, it's another case of network version fake news, and there's plenty of that going on. So remember, switches use MAC address tables, so we have to do some processing work to deal with IP addresses on our switches. So one of the things to watch out for with IGMP is that on some switches they use a microprocessor to do this on a CPU. And the problem with this is it's just running a piece of software, and it was probably never designed to deal with high-rate media information. It was probably just designed for doing printer discovery and simple things like that. So it's quite possible to overload some of these CPUs and cause very, very big and bad delays on your network. So it does mean that some switches can be absolutely terrible at dealing with multicast pruning. So what this can cause is it can cause unacceptable latency for clocking. It can cause terrible latency for audio, so you will never ever achieve the latency required to maintain synchronization, so the audio will drop. You can hear, sometimes you'll get chopping audio if it's an edge case, and you'll get devices losing sync. You may even see multiple master clocks if you're very unlucky. In terms of propagation, multicast is complex to do on certain infrastructures. So sometimes people ask for VLANs to be moved over a layer 3 core network. That can be very much dependent upon the performance of the device doing that. Often people try and do this in a software-defined network, and the processes just aren't fast enough to do this. Also, trying to put layer 2 over layer 3, as I said, many systems admins really don't like doing multicast routing. Multicast routing is difficult, and it's also backwards to normal routing. We don't advocate doing multiple subnet multicast routing at all. We have a solution for this called Dante Domain Manager, which takes the multicast aspect away from complex routed IP networks and makes everything unicast. PTP likes your forwarding delay to be symmetric and consistent. That's true of version 1 and version 2. Version 2.1 is in draft at the moment and makes some proposals, but they're not finished yet. Watch out for asymmetric technologies. You might see this as MPLS clouds. Also, passive optical networks are generally asymmetric. Passive optical networks do some strange reflection for multicast as well, so they become quite complex. A really common issue is badly configured access control lists within a switch fabric. Your typical symptoms when these happen are multiple PTP masters, and you'll also see devices possibly failing to maintain sync. One of the ways of finding out whether there is some strange multicast block in your network is to turn on unicast delay requests inside Dante controller. This means that the delay requests coming back on PTP go unicast instead of multicast. Now, if your multiple clocks disappear and suddenly become one master clock, that suggests that there is a bad multicast block inside your network infrastructure. Quite a few times we have used this to show an IT department that they have maybe misconfigured their network. Sometimes it helps not having that conversation at all, and it just fixes the problem and you can walk away smiling. But it's a useful tool. So, testing multicast switch performance. If you just create some Dante multicast flows in Dante controller, send them to a receiver, the next thing to do is check the latency in the Dante controller, and now turn on IGMP snooping in the switch. Now the latency will increase. It may only be a tiny, tiny bit. I've seen switches which only increase by a microsecond. It's no problem. And then increase the number of flows. What you're doing at this stage is seeing whether you can overload the processor inside the switch. Because if you overload the processor, the performance in time will go very, very non-linear, and you'll start to see very, very, very big delays because the processor is getting upset. On a nice switch, you won't see this happen. You'll only see a very, very small delay. Again, you can do the same for PTP testing. So again, create some traffic. Now look at the clock histogram in Dante controller. Now after you've turned on IGMP snooping, it is possible that there will be no difference to the clock histogram, which is a very good thing. That means you have a nicely performing switch. Again, increase the flows through the switch to see if you can overload it, and see if the clock histogram has started moving around. If it hasn't, you've got a very, very nice stable IGMP implementation. My personal method for trying out a new switch is I will try and acquire one from a supplier who will take a return, do this test. If it fails, I'll send it back and buy another switch. No manufacturer gives you enough hardware detail to give you any knowledge at all about whether their performance is good. You just have to test it this way. And trying to use a generic packet generator, don't do that. Normally traffic generators on operating systems are worse than what you get inside the switch. So using a dedicated piece of hardware like a Dante device, is actually very, very good for doing stable multicast packet generation. It gives you much better tools for actually determining what's going on. There are some telecoms companies using Dante devices to check the quality of their networks, because the timing information we get off a Dante network is actually more reliable than a lot of very expensive test tools. So a great question we get from a lot of our friends in IT is questions about bandwidth. And this is often, this has been traditionally the number 2 question that enterprise IT people have used when they don't want to look at a new service. So answer number 1 is it's bad for security. Who's heard that one before? Yeah, okay. And then you have a conversation about security and you find out how little they really know about it. It's a bit depressing, really. If you want a story about security with Dante, this is the funniest thing. The first time I ever worked with the Dante network as an end customer, I showed it on my talk yesterday. We did this thing for the British Armed Services in central London by St Paul's Cathedral, and our control point for the network was on the roof of the London Stock Exchange. So 2 days before the show, we showed up with racks and racks and racks of computers and switches and network cabling and fibre optic to the stock exchange, put all this stuff in the lift, went up the lift, wheeled it across the trading floor next to all the servers, set it all up. Nobody asked us a single question. That's network security for you. So next time you have a network manager talking to you about security, just remember that one. It's crazy. If I had known, I would not have done the gig. I would have done something else. So any project we're going to do with a network requires a certain amount of planning. For Dante, we need to know that we have enough transmit flows available to serve all of our intended receivers. We need to make sure we have enough bandwidth in the network to carry all of our flows. We need to make sure we don't have blocked logical connections. So if we go back to earlier, when we looked at TCP or UDP ports being like the individual cores in our multi-core, we need to make sure that they're not cut and that they're all working. And you know, they don't tend to buzz, but sometimes you might get contention. And you also need to make sure you have enough receive flows available on your devices to connect to the transmitters. So it's worth reminding ourselves what we put onto the wire with Dante. So in order to make the audio solution complete, we need to put audio transport, so that those are the samples, our audio samples that we put into those UDP ports. We have to put synchronization, so in the form of precision timing protocol for our clocking. We need to have device discovery, so we need devices that announce themselves to all of the other devices in the network to say, hi, here I am. And then we have to have commands that go across the network for routing and control. As we looked at with the layered network model, using IP over Ethernet means that we can do this very simply just on one cable. And of course there are some devices that quite happily take their power from this same cable as well. And the OSI model gives us a nice, easy framework to understand to do that tidily. So, in terms of project planning, we need to look at which other services we want on our network. We might want some kind of video service. We might want to watch movies. We might want internet access. We need to take into account which different services we're going to use, how much bandwidth they use, and whereabouts in the network they are going to use that bandwidth. We have to do an overall plan of what services our network's going to use. This helps us to specify the best infrastructure possible for our predicted bandwidth demands. It also helps us to identify those points in the network where there might be a shortage of bandwidth. And also we can then design around this to make sure that we have an architecture that, as the network grows, can actually expand over time. And then, of course, the critical part of any project planning, you have to be able to tell the future. Didn't anyone tell you? So yeah, being psychic, it's important. But luckily, there are some techniques that you can use to minimize your risk in terms of seeing the future. It doesn't help win the lottery, I'm afraid. I'm sorry, we're not that good. So this is typically what's going on in a Dante network. If I decide to send some data from, say, a microphone on device A, and I'm sending that to a mixer or a DSP, which is device B, I start immediately using 6 megabits per second of bandwidth in unicast. To extend our typical setup, let's send some more information from device C. Let's call that another microphone, and we send that to our mixer stroke DSP. We're now using 6 megabits per second down from each microphone and 12 megabits per second up into the processor. We're using 12 megabits per second in the backplane of our switch. Now, because our switch segments our collision domain that we looked at earlier, every single one of these network ports, if we call this a gigabit switch, has to be capable of transmitting and receiving 1 gigabit per second at a time. So in this case, where we have 5 devices, we have 5 1 gigabit per second ports. 5 times 2, because we have to send and receive, is 10. So our minimum backplane speed of this switch is 10 gigabits per second. So pretty quick. At the moment, we're using 12 megabits per second. So just over 1,000th of the capacity. So we don't have a problem yet. Okay, so let's start sending audio from our mixer to a loudspeaker. So we send 6 megabits per second down from our mixer up to our loudspeaker. And because it's stereo, we'll do that again with this device. And so we start sending 12 down and 12 up. So all straightforward, all very, very low bandwidth. This is also one of the things that is useful to consider when looking at an audio workflow as opposed to a video workflow. One of the things people in data networks forget is that in audio we mix sources together. Most people's first encounter of doing media over networking is normally CCTV systems. And if you try mixing video sources together, it doesn't work so well. It looks like a very dodgy 1970s pop video. Yeah. Whereas in audio, we mix sources together the whole time. So we can mix loads and loads of microphones together in this device B, but our outgoing bandwidth will never change because we're doing a mix here. Indeed, if I'm taking 1,000 microphones in one room, and I'm sending the mix of all those 1,000 microphones to another room, I'm probably only really sending 2 channels from one room to the other, not 1,000 channels. If that was video, I would have to send all 1,000 video cameras from one room to the other and use 1,000 times the bandwidth. So it's really worth bearing that in mind. It's not something that is obvious to network engineers, whereas to audio people, yeah, we mix signals all the time, big deal. So what? So yeah, just bear that in mind. It's not a linear proportionality. The most scary thing for people who ask me questions about using Dante networks is what happens if I plug in the internet? Well, there you go. That's what happens if you plug in the internet. These devices can't receive internet traffic. They're not interested in getting cat videos or anything like that. So they don't actually consume any bandwidth from the internet. There's no reason for them to subscribe to anything. So it can just sit there. I could do something really dangerous. I start watching, say, Netflix or some other movie streaming service on my laptop here. Okay, I start streaming 8 megabits per second down from the internet to my laptop. So that goes through this switch here, but I'm still using no megabits per second into the Dante part of the network, even though it's on the same local area network, same switch fabric, same VLAN. No problem at all. This is one of those classic examples where people get really, really worried and think they have to put the internet into a different VLAN. Well, what's the point? It's not doing anything. And also, you lose the ability to do this. If I put Dante Virtual Sound Card on, I can stream the audio from my movie back up to my DSP and get it to come out of my nice speakers. All I'm doing is sending 6 megabits per second of Dante traffic up into this network segment. These guys are still not interested in the movie content. It's just they have been told about some audio content happening over here that this guy should be interested in. And notice it's doing a mix, so this bandwidth doesn't change here either. that just stays the same as it ever was. So bringing in external media traffic is actually very, very trivial when you look at really what's going on with bandwidth in one of these networks. So remember, a Dante flow is the sequence of packets that we send from a port at an IP address, which we looked at earlier. So that UDP address that we used, which contains the audio samples. A single flow contains 4 channels of audio. On the little 2-channel devices, that will be 2 channels on the Ultimo 2. And at 48 kilohertz sample rate, that will use 6 megabits per second of bandwidth. Now, if only 1 channel is subscribed in that flow, the other 3 channels are sent as silence. If I had my marketing hat on, I would say that they came for free. But in truth, it costs you 4 channels to send 1. The nice thing is, if you choose to send some more channels along later, they will join at no extra cost. Now, the difference is a multicast flow will contain up to 8 channels. And a multicast flow will start consuming bandwidth as soon as it is created. Because a multicast flow has no concept of who is listening to it, it's just thrown out there, and hopefully someone will pick it up. But the network doesn't care. It will just use bandwidth. What happens here is this means that if I send 1 channel in a multicast flow, it will use about 1.5 megabits per second. If later I want to send a second channel as multicast, that will create a new multicast flow. If I want to do this efficiently, I should delete my first multicast flow, then create a new flow with the original channel and the new channel in it. That's much more efficient in terms of use of flows and use of bandwidth overhead. If you do that, you will lose audio for a short while, but Dante Controller will warn you about that. So generally, do not try reconfiguring multicast while you have a show on. It will not make you very popular. I promise you, I've done this. People don't like it. You think I'm joking? How do you think we learn? So a flow limit is the internal device limit that says how many channels we can send or receive. Different devices have different limits, and it doesn't matter whether the flow is unicast or multicast. A flow is a flow. Essentially, the difference is the destination IP address. That's the only difference as far as a transmitting device is concerned. So this is a breakdown. So for example, an Ultimo device can do 2 flows. The virtual sound card could do up to 16 flows. A Brooklyn 2 device will be able to do up to 32 flows. The high channel count devices that are coming out now can do up to 128 flows. Now this matters if I'm doing something like a broadcast system. So you can get a stage box that has 64 outputs on it. So I have 64 mic pre's going to 64 Dante channels. Typically, if I'm using a Brooklyn 2 style device, I have 32 flows available to me. And if I send those as 4-channel flows, I can only do a 2-way split before I run out of capacity. Sometimes that's okay. I could get a 32-channel stage box, same chipset, but only sending 32 channels. Now I can do a 4-way split, so I could do my front of house desk, my monitor console, I could do a recorder, and I could do a broadcast truck, and I'll be absolutely fine doing that 4-way split. So one of the design considerations may be that if you want to do lots and lots and lots of splits, go for a lower density stage box. So you can get stage boxes that do 8 channels only. On those guys, you could do a 16-way split quite happily. So if I was doing something like a multi-band TV show with lots of host broadcasters, I would go for lower density, higher flow ratio. If I was doing a small thing with just one colleague, I would go for higher density stage boxes. But it's an important consideration when you're looking at designing a network. So in unicast mode, a transmit flow is created when the receiving device requests 1 or more channels. And if room exists in an existing flow between the 2 devices, that audio will be added to that flow at no extra cost. In multicast flow, the transmit flow is created immediately and is just sent to that destination, and you can't add channels to a multicast flow. All Dante channels are unicast by default. As we've seen, if you have a network that does not have IGMP snooping enabled on it, that traffic will go everywhere. So it is more polite from our point of view to create unicast all the time, and it be a deliberate decision on the part of the user to use multicast. Only intentional programming can create a multicast flow. Dante does not do it automatically. We also discourage our manufacturing partners from doing an automatic multicast mode. Like I said, you only learn by doing. Many years ago, there was a product that did automatic multicast. And yeah, it caused some problems. And that feature was removed after we made some comments about it killing a rather big show. But yeah, hey, everybody learns. So yeah, be careful about just throwing stuff out as multicast in general. However, using multicast is very useful when you want to send the same audio to many different destinations. So if I'm doing something like a big stadium, I would want to send, say, one multicast group to maybe 100 amplifiers. There is no point in sending it to sending loads of unicast containing the same information. That's bad networking right there. If you're going to create multicast, plan ahead. It's very difficult to just randomly create multicast and be efficient. So yeah, have a plan when you're going to build it, and certainly configure multicast when nobody's listening to the system. Using the transmit flow visibility in Dante Controller is really useful. So if you look at the transmit flow for a device, it will say how many flows you are using and how many you have left. There are no secret hidden ones. That number is totally honest. If you want to make transmit flows more efficient, you can use multicast to do this. Make sure that you have enough receivers available as well. So, for example, the same thing. If I have a mixing console which has 64 input channels, but it only has a 32 flow capable device, that's fine all the time I am using multiple channel stage boxes. But if I plug in single channel microphones, suddenly I only have 32 microphones available. So be slightly careful and knowledgeable about that as well. So a quick recap. Audio networks consist of three things. We have things that create flows, which could be microphones, DSPs, playback devices. We have things that receive flows, which could be also DSPs, could be speakers, could be recorders. And then we have stuff that connects networks together in the middle, say switches, routers, and cabling. So we'll look slightly more visually at the subscription process within Dante. This makes it a bit easier to understand. We'll look at multicast subscriptions, and we'll look at how topology is really a much better way of managing a network than using QoS. So this is what's really going on in Dante Controller. I'm running Dante Controller on this laptop. So I plug the laptop into the switch, and I see nothing because nothing else is plugged in. Dante Controller is a real-time view of what is happening in the network. I plug my microphone in, and the microphone sends out a multicast message to everybody saying, hello, my name is Bob, in this case. And you will see that. If you use Wireshark, you'll see something called an MDNS announcement, and it will just have the device name on it. And it could be Bob. Maybe. Now, this multicast message is picked up by Dante Controller that's listening for that multicast IP address, and it will put the name Bob onto the screen in Dante Controller. Next thing I do, I plug in my speaker, which I've called Paul. Same thing, it sends out a multicast message saying, hello, my name's Paul. Dante Controller sees that and adds Paul, the loudspeaker, to the matrix. So, now I want to do a really unique thing. I want to send audio from the microphone to the speaker in the normal way. So Dante controller sends a message to Paul saying, Paul, can you please subscribe your channel 1 to channel 1 at Bob? So that message will go directly from Dante controller to the speaker, and that will cause this device to send a message to the microphone saying, Bob, can I have channel 1 at 1 millisecond latency, please? Now the microphone will ask itself the question, can I achieve a 1 millisecond latency? If it can, it will send it, but if it can't, it will say, no, here is channel 1 at 2 milliseconds latency, and the speaker will receive it at 2 milliseconds latency. So depending upon the latency setting of this guy and this guy, we will use the longer of the two latency settings to form that connection. When that's all good, another multicast message will go out from Paul here saying it's successfully subscribed to channel 1 at Bob, and that will cause Dante controller to show that nice green check mark. The reason why this is a multicast message for that is because when we send multicast, we can have multiple controllers plugged into the same network, and they can all update from that same multicast message. So yeah, fairly simple. It is receiver orientated in terms of setting up in unicast. In multicast, it's actually transmitter orientated, so it's the other way around. On the transmitter, we set up a channel to go, and that's it. It's just thrown into the network, and then it is up to the other devices to connect to that multicast group or not, as it appears. Dante cannot dynamically switch unicast to multicast, but if you create a multicast flow after a unicast subscription has been made, it will be moved over to the multicast flow if there's an opportunity to do that. So let's look at some topology examples. So I have a bunch of Dante-enabled devices here. I've got 14 devices, each one has 64 channels. Each of these could do 32 flows maximum. So their maximum bandwidth is 192 megabits per second. Now that's not practical in this network, but we should always calculate to the worst case scenario. So 192 times 14 gives us 2.7 gigabits per second, basically a lot more than a gigabit. My maximum receive bandwidth per node is still 192 megabits per second unicast, otherwise I would run out of flows. Now because this is all unicast traffic, we're quite safe here. Okay, so the maximum I can ask for as a receiver is 192 megabits per second. Because this is a non-blocking switch, and this has 28 ports on it, sorry, 14 ports, it has to have a minimum backplane speed of 28 gigabits per second. We're sending less than 10% of the backplane capacity into this switch. So we have no problems with blocking in the switch. We've got 90% free. We can't receive more than 192 megabits per second per device. So this works absolutely fine. Okay, so people talk about in theory it could be greater. No, it can't. That's impossible. This switch is absolutely fine. It's working at less than 10% capacity. This network is absolutely fine like this in unicast. Even if we did the worst job possible, we'd still only use 32 two-channel flows on maybe 1 or 2 devices here, and that would be hard. But we only have a 2-way split achievable if we do that kind of thing. So, let's make this worse. Let's set all of these devices to full multicast. Now we could have a problem. So the switch is still going to be fine, and in fact the amount of bandwidth in the switch would reduce because we're not being inefficient with flows. All we're doing is we're sending, single multicast flows containing single channels. We're great. The devices aren't going to be very happy because if we sent 8 12 megabit per second multicast flows, so that would be 8 channels times 8 is 64. Each of those channels would be 12 megabits per second. and we do that by 14 nodes. The actual bandwidth we're using drops to only 1.3 gigabits per second. But if we don't manage the multicast, we're sending more than a gigabit per second back to every single one of these devices, and we end up with a complete jam happening because we just don't have the bandwidth capacity. We're still only using 4.8% of the possible bandwidth of the switch. Is nothing. So what we should be doing here is turning on IGMP snooping. That would immediately solve our problem. That would suddenly drop us back down to a very, very manageable amount of bandwidth. Remember, we're sending 832 channels of audio here. That's not an insubstantial amount of audio traffic, okay? Most people don't do networks that size. So I should be able to have a switch of IGMP snooping on. I turn that on, my problems go away. So, turn on IGMP snooping, problem solved. A much, much, much more significant way of dealing with this bandwidth problem than trying to do QoS. Most of the time, people try to do QoS first. There is a problem. Always try to sort out IGMP and multicast management first. It's normally the cause of most bandwidth issues with audio. So, always, always, always do IGMP first over QoS. Right, so let's look at a totally ridiculous scenario. Let's double the size of the network. We've now got 28 devices here. We've got 14 devices at the top, and we're sending on a one-to-one mapping from these devices down to these devices. Even if we do this unicast, we're trying to send 896 channels of audio down this one cable. 16 flows per device. We're using 1.344 gigabits per second. If this is a 1 gigabit per second cable, we have just run out of bandwidth. There's nothing that quality of service can do, because quality of service cannot create bandwidth. So, simply put, we've just run out of bandwidth. Just use a 10 gigabit per second link. Now, the sensible thing here is that we're dealing with 896 channels of audio going from here to here. Let's consider a 10 gig link is going to cost maybe $500. Yeah, and that will carry 6,000 channels. How much do 896 microphones cost? It's going to be, you're talking probably $6 or $7 million of gear to get that number of channels. So $500 for a 10 gig link is nothing. So the proportionality of price and bandwidth for audio works very, very nicely. Money is not your problem if you have a system this size. So we have different models for dealing with different styles of network. That previous example showed a bottleneck being created by just one pinch point. In big networks, we have something called the classic or three-layer hierarchical model of a network. And this is where we have edge switches, and we have a distribution layer, and then we have a core layer. Now, the idea of this technique is that cores should only connect to other cores. The idea is you shouldn't really ever send traffic across a core, because that should be handled by the distribution layer. You should never get to the core layer unless you're going from one core maybe to a different building through the core. Furthermore, you should never do traffic shaping or filtering in the core, because that should happen out towards the edge. So the core part of the network is just there for forwarding packets as fast as possible. All of the noise reduction and everything should be done on the outside. So this is the ideal model to use for a large network, and typically audio applications happen out at the edge here. They don't normally go across cores, or very rarely, not in high density. So if my meeting rooms in one building are out here, they would all be centered around this area, and I might be sending one or two channels down here, and they might go across here, but they would never cross the core. Now, of course, as switch speeds have increased, and because people like to talk about new marketing buzzwords for the same old concept, we have this thing called a collapsed core model, which is a flash way of saying I've got a very, very fast switch, which means I can put my distribution out to the edge and pretend that I don't need it, which is okay until you start putting video into the network. So the new proposal with video is to do something called a spine and leaf topology. Well, that's what they call it at the moment, where we have a super fast backbone between different collapsed core switches, and it looks very suspiciously like the 1970s model of a mainframe network with a backbone, but it's got a different name. Networking. Same things, different names. If you want to predict the future of networking, look at the past and just change the names of things. Like all computing. Yeah, we had mainframes, but that's all right. Then we had the desktop. Then we've got the cloud, which is definitely not a mainframe. Not at all. It's a different word, okay? And so if anybody can come up with a new word for desktop, trademark it, and sell it to a big vendor, because that's where we're going next, I'm sure. As the next generation of processors come around and the processors get faster than the network, we're going to have this outward thing towards the edge or the desktop of the network. And then when the network catches up in speed, we'll go back towards the mainframe or cloud, but we'll call it a different name in 5 years' time. It's always gone like this. It's been like this for the last 50 years. It won't change. One of the things that's interesting about what we do with networks is synchronization. So this is about how we synchronize media clocks. And, you know, there is a lot of talk about external clocking for devices. So what we do with the Dante system is we synchronize time and not clocking. This is useful because it means that we can synchronize different kinds of services. Does everybody here know what a phase lock loop does? Or is this a new term? Yeah, it could, because a lot of the time when I talk about this with people, people are like, what are you talking about? And it's okay. I actually enjoy this part because it's funny. We have a good time with this. So most of us have heard of word clock, which is this low rate signal here. How many people drive their own car here? No? Nobody drives? No? Okay. Well, if you're in a taxi, say, okay, when you're traveling down the road, it's considered polite not to crash into the person in front of you. Yeah? So this is what we would call a reference. So if I'm driving my car, the car in front is my reference. That is the point I should not touch with my car. And that is what this external word clock is. So here we go. This is like the car in front. This is the back bumper, and I'm behind it, so I mustn't hit it. I need to get as close as possible to it without smashing it. So this is what an external word clock and what a phase lock loop does. So there was some mystery. People were under the impression that using an external word clock was the same as taking the clock from inside my device and replacing it with something from outside. This is like saying that the guy in the car in front is somehow magically getting out of his car and controlling my car, and I have to get into the passenger seat. That's not what happens. What I'm doing is I'm carefully watching the back of his car, and I'm using the brake and the gas to make sure I don't smash into him. So here's a reference, and he's controlling the speed I choose to move at. And this is exactly what an external word clock is doing to my internal word clock. It doesn't replace anything. So the mental process, what my brain is doing, hopefully, is slowing down and speeding up so I don't crash into this guy. And that's what a phase lock loop does. And I come out of the other end of this phase lock loop process, and I stay perfectly synchronized and a perfect distance from the guy in front. So we've all been traveling around, and sometimes we see a very bad driver in front of us, and they're speeding up and slowing down. And if we followed them very, very closely and sped up and slowed down at the same rate they did, we would feel a bit sick. And certainly if I'm taking my grandmother to the shops, I would not want to do that. She would get very angry with me. So I apply some intelligence, and I go, that guy is an idiot. I'm going to stay a bit back from him, and I'm going to be much more gentle. So I can drift closer, but not dangerously close, and I can stay away from him and stay safe. And my grandmother is not going to get angry. The nice thing with that is that my ride is much, much smoother, and just like in a word clock situation, my jitter is much, much lower because I'm not following a bad reference. So that's something else that a phase lock loop does very, very nicely. And this is important because this happens with crystal oscillators inside devices, and it's also very, very important for what we do for synchronizing devices across a network. Because a network can be quite a heavily jittered environment, and we don't necessarily want to blindly follow the bad driver that is looking like they're a worse driver because of the network conditions. So a network is like having a road that has big holes in it, and everybody's having to drive around the holes randomly and in a scared fashion. We have to make sure that we're not responding to this in a bad way. We have to kind of be chilled out and calm. And that's a really, really important thing for network synchronization. So in a traditional clocked network, we would have a master clock device which would send out a constant rate word clock. So if you look at a broadcast style serial SDI clock source, it would send 48,000 pulses per second for 48 kilohertz over a cable. Now earlier on I said that Dante manages to maintain a synchronization of 1 microsecond anywhere in the network. Well, that's great, but if I look at how long it takes for the data to go down the cable, I can see that I can only travel 280 meters in 1 microsecond. So how can someone come along and say, oh, I can guarantee 1 microsecond synchronization anywhere in the network? Because, you know, you haven't told me how big your network is. It could be 1,000 kilometers across. And yes, we do deal with networks that size. And yes, we do maintain synchronization of 1 microsecond. So there are many, many, many people in the audio business who will claim to break the laws of physics. We don't. The reason we can do this kind of synchronization is because we do not distribute clock like this. We distribute time. So as long as we can get the time accurate between places, then we can generate a clock locally, and we can create that synchronization by deriving our clock from time. So, how do we do this? This is what 1588 does. PTP, or IEEE 1588, is concerned with, don't tell me how the clock works, just tell me what time it is. And after that, you can define whichever clock you like. This was a problem that was really solved in the 19th century. So like all things, let's give it a new name. So we have various problems in the UK, but somebody thought once upon a time it would be nice to have a railway timetable. I still think it would be nice to have a railway timetable, but we can try. They're never on time. Anyway, so in the 1840s, we had these wonderful things called trains, but we didn't have a way of communicating on wire or even wirelessly between cities. So there was no way of knowing what time it was in London precisely with what time it was in Edinburgh. So the problem was solved by taking a train, getting a reference clock, so a big clock there, getting a watch or a small clock, setting the time identically, jumping on the train, you go to the first station, you get out of the train, you set the clock at the station, you get back on the train, go to the next station, set the clock at the next station, carry on doing that at every station all the way up the line till you get to the other end in Edinburgh, set the clock, and then go back again and get out at the next station down the track and look at how much the time has changed by. Now, it will have changed at a different rate to your reference because the clocks are not stable against each other, especially not swinging tick-tock pendulum clocks. So what you would do is you would adjust the speed of that clock to go faster or slower, then go to the next station, do the same process. And after going up and down the track a few times, you would get those clocks to be rate identical, so they'd all be moving at the same rate, and you would get them to be time identical. So just by checking them over and over again, you get high precision. And that's exactly what PTP does. It's just we do it with the data network, and we do it using multicast. So yeah, not a new problem to have to solve. And actually, the best problems are simple. So we can obtain very, very, very high timing resolutions with PTP, and the timing resolution of PTP is in nanoseconds. So the problem with a physical clock is we have to unload it from the train every time, and we can only do this at one stage at a time. This is why we use multicast messages. First of all, we know that it left at precise time from a single point in the network, and we can get an idea of its propagation time by looking at the multicast messages. Also, on a data network, it travels a lot quicker than on a train. So this is what happens. We first of all send a message saying this is a sync message. We give the sync message a reference number, and we tell it what date and day and time it is. In this case, it's 9 o'clock in the morning and 1 second and some nanoseconds. The slave devices hear this and set their outside clocks to the same time. And then I send a follow-up message saying when that message was actually sent sometime later. That gets across the network. And now the slave devices can go, well, actually, I can see how long the difference between the time where I am and the time at the sender was. And I can look at that. So this guy says, oh, I counted 1,410 nanoseconds between these times, speed up. And this one counted 1,445 nanoseconds between these times, slow down, because the actual amount of time was somewhere between. So we saw how frames can potentially get in the way of each other in quality of service. Now, if I get two frames hitting the switch at the same time, in a switch we'll just queue them. In a hub they collide and they cause problems, but in a switch we keep them separate and we buffer them. So what we have to do is we have to consider what the maximum possible delay of a frame is. And what we're concerned about is maximum possible delay. So we take the maximum possible size of an Ethernet frame, which is 1518 bytes. And if we divide, if we take 1518, times it by 8 to get bits, then divide that by 1 gigabit, we get a value of about 12 microseconds. So 12 microseconds is the maximum time that a delay can happen on a gigabit switch. It's not actually a huge amount of time, especially with running a low-rate mechanism like PTP. It's fairly transparent. In fact, it's always smaller than that, because if you look at how big a PTP frame is, it's about 1/10 of that size. So the delay time on a PTP frame is going to be about 1.2 microseconds, because it's tiny. Most traffic is not maximum transmission unit size. Dante is typically about 1/3 of maximum transmission unit for audio packets. But we need to get an average of the time going across the network. We won't just take the first value and run with it. And we also need to get an idea about how long it's taken the traffic to get across the network. So we do a reverse process called delay request messages. And this is why we have a certain scale to the number of devices that can be slaves in a particular subnet. So with something like a Brooklyn 2 device, we can manage about 200 different slaves. With something like an Ultimo, that number is slightly smaller. It's going to be somewhere between 20 and 30 devices. And this is because the slave device sends back a message saying, here's the delay request message. It has a reference number again, 1066. And this guy's saying it's 9 o'clock in the morning, 2 seconds and some nanoseconds. What time did you get this? And the master sends back a response message saying, okay, I got your message 1066, I got it at this time, and I sent you the reply at this time. And that gives us an idea about how long it's taking those messages to get across the network. So the nice thing about PTP as a mechanism is because it deals with distributing a real, what we call word clock, a hour, minute, second, day, month, year type time, it means that every single device has a concept of exactly what wall clock time it is. And that means that every device could potentially take over as the master clock device. So that means if our main master clock disappears, if we're using an entirely PTP-based system, it doesn't matter because everybody knows what the time is. We can move master clock seamlessly and not worry about it. So in a Dante-only network, it doesn't matter who the master clock is because everybody within a very, very short amount of time has a very, very accurate idea about what real time it is. So this is a thought experiment. In older broadcast systems, people are always worried about adding some kind of master clock device to synchronize devices. Like I said, I have very little time for technology's sake, but there is an argument saying that IP is the future. If it is the future, and that is not for me to decide, one would hope that the amount of content to be generated in the future is greater than the amount of content that was generated in the past. Otherwise, there would be no point in updating technology. So maybe it would be a good idea to have a network-centric synchronization method, as in the system that's using SMPTE 2059, which is basically reliant upon PTP, like we use with Dante, which will synchronize SMPTE 2110, which Dante will support for broadcast, and synchronize all of those things based upon PTP, and then synchronize the legacy stuff with the old-fashioned SDI system, but that master clock will take its synchronization from the network, not the other way around. Because logically, if you continue to use a old-fashioned traditional master clock, the time you turn off that traditional master clock will be that last day where you decommission that very last video deck that you kept just in case you had to play back video in 40 years' time, when all the cameras have gone, when all the switches have gone, when everything else has gone, and you've just got that one device left. Whereas if you start today disciplining everything from the network to the old system, it means swapping 2 cables over. Then you can carry on with a future perspective. You maintain the resilience of the network side of things, but you're at no less of a disadvantage with your legacy systems. It's a thought experiment, but it's definitely one worth having. Right, I think that we should probably take a 15-minute break. Pretty much the last section that we have on this fairly intensive course, I'm going to talk about troubleshooting. So, of course, networks, just like any audio system, are about connecting devices together. And normally, as we know from doing analog audio, if something is unplugged, generally plugging it back in again correctly solves the problem. And really, it's just the same with a network. Just an idea about what we're putting onto the network. We're putting timing, so PTP, which is IEEE 1588. We're putting audio data into the network. We're putting in commands to create routes and control Dante functions, and we're using discovery services so that we can find devices in order to send them the commands. So this is sounds a little bit philosophical, really. Just because you can't see it doesn't mean it cannot be seen. What that really means is that, remember that when you are looking at a network with Dante controller, you are using a computer, and the Dante controller is an application sitting at the very, very top of the network stack. That means that there is a possibility that your computer operating system may have put a firewall into your network path, and it may be just something as simple as your computer blocking visibility to the network. So the first sanity check, and I've had this happen to myself, if I can hear audio on the network between my loudspeaker and my microphone, and Dante controller is telling me that there is no audio coming out, do I believe my ears or do I believe my eyes? And this is a continual complaint from audio engineers about people trusting computer screens. If there's sound coming out, it's probably okay. A very, very big stadium project I worked on once, we had this debate about quality of service, and apparently telling them to turn off the quality of service was the wrong answer. This was a dedicated network, Dante only, and there was no sound coming out, and it was for an evacuation system. And so, you know, the integrator had done all the right things. They'd asked for a network expert to come along and set the switches up. There's no sound coming out, so I said, look, first thing we need to do, let's turn off all the quality of service and see if we get sound. Turn it all off, there's sound coming out of the system, perfect. We go and test everything for redundancy, everything's absolutely fine, the fire inspector is totally happy. The guy comes back, the network consultant's like, no, these are all the wrong settings. Goes back in, puts all his quality of service settings back into the network, no sound. Now this really depends on your point of view of what's right. The fire inspector thinks that the sound coming out of the evacuation system is a correctly functioning system, and not having sound coming out of the evacuation system is really bad. I would tend to agree with that, actually. So any configuration of the system that stops it working, I would say is wrong. That could be considered old-fashioned. So yeah, in the end we turned off all the quality of service. It was absolutely fine, and to my knowledge it's still working now, 8 years later. In fact, there was a blip in the middle where somehow this guy had come back, restored the settings, and suddenly it was all our fault 4 years after it achieved its certificate, went back in, removed QoS again, it's all working again. And so really, some people think that correct is something on the screen rather than something with their ears. With a sound system, sound is definitely right, okay? I think. Keep it simple. Firewalls, what we do with Dante is that when you install Dante controller or Dante virtual sound card on a Windows system, we reconfigure the Windows firewall to allow the traffic that we need through the Windows firewall. We don't do that for any other third-party firewalls because we don't know all of their APIs. So if you are going to put a third-party firewall into your Dante network, these are the magic numbers you need. So that's on your handout there. So this is basically a network wiring diagram. So let's break this down. MDNS, this is the discovery channel, and I don't mean it's got cute animals on it. This is basically the IP address and port number where that message, hello, my name's Bob, hello, my name's Paul, shows up. So if I was looking at my floor of cabling, I would find the multi-core with 224.00251 on it, pick it up, and find the pair that's marked 5353, pick that up, and as long as I could plug that into my Dante controller, I know I can discover those devices. Fairly straightforward, that's all I'm doing. The next thing I'm doing is controller monitoring. So again, I would look for my multi-core that is labeled 224.00230 and the other two, 231 and 232, and then I would look for these cores 8007 to 8706, so quite a lot of cores there, and those are my control and monitoring channels, and they can come from lots of different IP addresses, so they will be coming from all of the different Dante devices going to this particular address. The next thing I've got is my PTP traffic. Now PTP is sent to 224.01129 and it uses 30, 31 and 32 as well, and it always uses ports number 319 and 320. So those are the cables I have to have plugged in to do PTP synchronization. My multicast audio lives in this huge address range here. So there are potentially 65,536 multicast flows available in a Dante subnet. So a huge number of channels. And they're always sent to port 4321 because someone was feeling very imaginative the day they wrote this and thought 4, 3, 2, 1, there we go. That's the only reason. Unicast audio comes from the receiver's goes to the receiver's unicast IP address and is sent to these ports 14,336 to 14,600. So that's where all of the Dante unicast audio lives. AES67 multicast audio can be changed. So by default, we would use this IP address range 239.255.00/16. Basically because this particular IP address range is special. It's called the local administratively scoped multicast IP address range. Sorry. It has a special meaning. Basically, it means that a systems administrator can use those multicast IP addresses in their own network. They won't go across the public internet, but they're super flexible for internal use. Some implementations of AES67 go outside this range, so we allow this octet here to be reconfigured because there are some IP addresses outside this that people believe are useful for AES67. To avoid having a big fight about this, we've just made that user configurable. We would advise to use this range, but other people think differently, so that's fine. One thing to note, all Dante traffic is UDP, so we don't have a TCP stack. That's quite nice because TCP is a slightly easier transport layer protocol to hack. UDP is more difficult because it doesn't always reply. It also means that our attack surface is half the size because if you're doing a Dante only network, hey, you can just happily block all TCP traffic, no problem. It doesn't affect us. So if we're using a firewall, we're just looking for where the firewall is cutting the wires, and it can be cutting the wires at the transport layer, so it could be cutting port addresses on the TCP or the UDP part of the network. It could be blocking entire IP addresses. It could be blocking entire IP subnets down at layer 3. And then Mac-to-Mac communication further down is something that you might manage in a switch. It would be unusual to do that in a computer, but not impossible. One thing to watch out for also is antivirus programs. They can have an element of network interaction. So if we consider something like a Trojan horse virus, which will send data to a random IP address, or at least an unknown one, and unknown socket addresses, that could look very much like Dante Virtual Sound Card. Because Dante Virtual Sound Card, after all, is sending data to unknown socket addresses. It's not a well-known service yet. So sometimes we have found that firewall and antivirus software can cause blocking of audio and also of device discovery. So something to watch out for there. Generally, if you can absolutely guarantee that no machine is ever going to leave your network, which in live sound is basically impossible, but in some corporate systems is entirely possible, having a firewall appliance at the edge of your network is actually a much more robust way of defending your network than having firewalls on every single machine. But you need to make sure those machines never leave, and that's sometimes quite hard to do. But certainly, I use the equivalent of if I'm driving a Formula 1 car on a racetrack, nobody lets a Hyundai taxi come on the racetrack, do they? Because there would be a bad accident. Same thing with this. We have a high-performance network that we want to send audio and video around. We don't go putting a police checkpoint in the middle of the home straight where we're trying to do 200 miles an hour. That would be kind of crazy. What we do is we make sure we've got a big security guard at the edge of the racetrack going, no, you're not coming in. And that's exactly what you would do with a firewall appliance. If you want high performance, manage the security in the appropriate places. Going further down into the switch fabric and also where the routers are, we can use things called access control lists. They're very, very powerful for filtering different kinds of traffic in the network. Many, many advanced IT networks will be using access control lists. A general tip is I have never ever asked a IT department what their access control lists are, simply because first of all, they shouldn't tell me, and they probably won't tell me. And third, that I will probably make them very angry if I do ask them, because that's a very amateurish thing to do. So yes, you have to assume they probably are using access control lists, and they won't tell you. So the best thing to give them is this list here, and go, of course you're not using access control lists, but if you were, you might want to consider these numbers. And then they will disappear and go very quiet for a few hours, and then sometimes things start working magically. Oh, this is fantasy world. It is reasonable to expect that an IT service is provided for, essentially, when you're working in a corporate environment. At the end of the day, if I'm putting in a meeting room for a company, it seems reasonable that the company paid for the meeting room, they want it to work, and it's really the job of the IT guys to make that work. Sometimes IT guys don't believe they are in a service industry. What you tend to find is AV people are really, really service orientated. They want to do a really good job. They want to make things look good. They want to make things sound great. They're not actually very used to telling people no. Lots of IT people turn around and say no to people all the time. It's changing. It's getting better. But yeah, it's on the trailing edge of a service industry. And it's fair enough. It's a very, very difficult job. Trying to manage all of the computer services in an organisation is really difficult. Has anybody got angry with the IT department because the email's not working? I do it all the time. Actually, it's got better. They actually fixed it. We haven't had an outage that's been their fault for 2 years. We did have an outage that definitely wasn't their fault a few weeks ago. But that's because Microsoft took out most of the world for a morning. Which was great fun. And yes, of course, initially I blamed our Australian IT people, and I phoned them up in the middle of the night, and they're going, "Oh, what? No, we haven't done anything. We've been asleep." And then, an hour later, the head news starts coming up that Microsoft have had this huge outage, and I'm like, "Oh, sorry, you go back to bed now." So yeah, IT guys get a hard time from everybody, especially if they work in an IT-centric company. For quite a long time, Audinate were getting through IT managers very quickly. The average life expectancy of an IT manager was about 6 or 7 hours. Can you imagine trying to walk into an R&D department of computer scientists and go, "No, we're going to do it this way"? Good luck. You're just going to have a massive argument. They're going to go, "No, I invented that. It's staying." And then, no, that's staying. Right, okay, I'm fed up with this. I'm going. So we got through tons of IT people. So we do know what it feels like from the other side. IT people do get very, very upset easily. Then we got a really good guy who was just like, "I don't care what you think. We're doing it this way." And after some pain, it's okay now. So it's definitely a two-way street with IT departments. They're not all bad. Watch out for multicast IP addresses. Because they only work in a single IP subnet. In theory, you can do rooted IP multicast. Yeah, friends don't let friends do multicast routing, okay? It's really hard, and it's very depressing. So we try to make it as easy as possible to avoid it. So when you want to do multiple subnets with the Dante system, do everything unicast. And we can do that using the Dante domain manager to sort all of that stuff out for you. We have seen people do multicast routing, and we're very, very impressed with them doing it, but really I would not want to inflict it on my worst enemy. Watch out, because some switches will block certain legitimate multicast IP addresses by default. We saw that before with those switches we called out in the multicast section. You might block Dante discovery, so devices may not appear. You might see multiple clock masters appearing. That's a surefire indication that multicast is being blocked. And you might not get any Dante multicast audio. So unicast IP addresses will generally only be blocked by an access control list or a firewall, or the absence of a root between subnets. Just one pro tip here, when you're setting up routes between different IP routers, always check the subnet mask. I still screw that up myself all the time. My preferred router always defaults to a host route or 32-bit IP subnet mask, and about every other time I forget, and I get very angry because I can only ping the gateway because I've just set up a one host only network. So yeah, always check that. I mean, it doesn't matter how long you've been doing it for, it still goes wrong. MAC addresses very rarely cause any issues unless somebody is trying to do a deliberate MAC address filtered security system. I don't see these very often. In fact, we should probably see MAC address filtering more often than we do in secure networks. There's been a lot of scaremongering about this concept that we can spoof MAC addresses. Well, it's not really an excuse for doing nothing. It's an excuse for understanding that it's not a perfect security system. I do deal with one particular institution that are very, very hot on this kind of thing, and it's one of my top tips for network troubleshooting. If I take a new device to this institute, I can't do anything with it for at least 25 minutes. I have to basically plug it into their network, tell their security guys I'm there, and then leave it. Which is a good opportunity to go and get a cup of tea, hang around for a bit, then come back 20 minutes later, everything works fine. It's also a good idea when you first commissioned a network. When a network starts up, it's doing lots and lots of functions for discovery, and the forwarding tables are all populating. Now this happens very, very quickly. It happens in milliseconds. But sometimes it's a good idea just to let the whole thing settle down for a little while, because you can start battling problems that don't exist. I mean, certainly the first 2 minutes of a network being up, do not touch it. Especially if you're using something like spanning tree protocol, that takes time to settle down. It is a temptation to panic when you're trying to commission a big network. The most important thing is patience. And definitely having a cup of tea is a really, really good idea. It's saved so much time. And down at layer 1, just check simple things. Is the wire physically cut? Is it plugged in? I mean, again, I'm trying to remember the last time I forgot to plug something in, because it's normally only days away. And you've got so much on your mind that you forget to plug something in, especially in a complex system. You run around like a crazy thing, and then it's, oh, okay, yeah, there we go. That's working now. Who hasn't done that? No? Yeah, exactly. And the best thing I ever bought using fiber optic, I bought a proper fiber tester to look at the loss of signal down a long fiber. Saved so much problems and really stopped us losing some major contracts, because it stopped us sending broken fibers out onto shows. So just run everything through a quick tester. It tells you whether you've got a good cable or a bad cable, and you have to do that with an optical power measurement tool with fiber. You can't just look at it. Similarly with copper cables, Cat5, Cat6, Cat7 cables are not Cat5 or Cat6 or Cat7 until they have been tested in situ. It may say it on the outside, and that means nothing. Until they've passed the certification exam in situ, they're just a piece of wire. We did have this, and this is the most frustrating thing on the physical layer. We had this mystery happening. We had a customer report that they had some crackling happening on a show. So, okay, well that's really bad. And it turned out they had taken a 64-pin Veeam connector, an old analog connector, and put 8 Cat6 cables onto it, and then got an 8-way Cat6 multi-core, and plugged this all in as a multi-way Category 6 loom. The problem is, in that kind of assembly, you have 12 centimeters of parallel connectors. And so you have insane crosstalk. But they said, well, but it says Cat6 on the cable, it must be Cat6. And it's like, it really isn't. We stuck it on the tester, and best cable failed by only 40 dB. The most annoying thing was, it only lost about 5 or 6 samples every 6 hours. Under those circumstances, I really wish it had done nothing and just broken. That would have been better. So, yeah, sometimes it will work down a wet piece of string, as we say, and that's really depressing, because under those circumstances, you just wish it would break, and proper break. So it's very, very robust technology. You can do some really stupid stuff with it. It doesn't mean it's a good idea. Second time I used this, I was working with a colleague who didn't understand how to measure architect's drawings, and I was assured that our run from the stage to the control position was 80 meters. It was 180 meters, and we were on Cat 5. There's nothing clever about using out-of-spec cables. I spent 4 days worrying about losing audio. It was horrible. I would not wish that on anybody else. Stick to the 100 meters. It's there for a reason. That's the best advice with a physical layer. Just, you know, yeah, I've never been impressed with running something longer than it should do. So some common symptoms. You might see a device name in Dante controller, and there may be no plus sign to help you open up to see all the channels. What that normally means is that the firewall on your computer is turned on and is blocking that particular port transaction. The other thing that may be happening is your computer may be in a different IP subnet to the device in question. Now, the reason why you can see the name is because it is advertised as multicast, and like we said before, we have to cheat with multicast. We have to allow the network stack to listen to multicast IP addresses, even though they are not in the same IP subnet as my device. So when Dante controller sees a multicast name advertised, it goes, aha, okay, so there's Bob the speaker over there, and Bob's advertised as Bob on this multicast channel, and it also says what Bob's IP address is. And Dante controller will try to talk back to find out more about Bob using that unicast IP address. If you're in a different IP subnet, that can't happen, and Dante controller won't populate. So it's worth checking both those things, the firewall and also which IP subnet your controller is in. Sometimes you can get an unlock or lock warning. Now, this is possibly a symptom of a multicast block in the network. So have a look at the clock histogram in Dante controller to see if it's moving around a lot. If you turn on unicast delay requests in the device, which you can do from the device configuration screen, and that problem goes away, it's almost certainly some kind of multicast block inside your network. One thing to watch out for, and this is a key thing about implementation versus standards. So we talked about how we do sync messages and follow-up messages in PTP. There are some things that we do with Dante to make sure these things are super stable. So we were looking at a phase lock loop, and we're talking about having a crazy driver. What you want is you want a driver who's just like you. Now, hopefully they're just as crazy or just as sane as you are, but they need to be similar to you. That's the important thing. So what we do is, when we design Dante-enabled equipment, we specify a particular clock synthesizer chip and a particular crystal for every single Dante device. That's the same on every device that's ever been made. The advantage with doing that is it's very, very easy to model the physical characteristics of that clock system. So this can be a good thing, because it means we can get very, very rapid synchronization because there's very little variance. And it can be potentially a bad thing, because once they're synchronized, they stay synchronized. We did see a system, a broadcaster, where the IT guys had messed with the network, blocked the multicast, and the system had stayed in sync for 3 days without a reference coming in. So 3 days later, the audio broke. They, of course, started screaming and shouting because they lost all of their audio feeds. And so I was talking to them and said, look, guys, something must have happened to the IT infrastructure. And no, the IT guys have not been in for at least 3 days. let's look at what they did 3 days ago. Oh, they've blocked multicast. That's what caused it. So why did it take 3 days to happen? We're using the same crystal, the same synthesizer chips. This is in a broadcast sensor where it's in a thermally controlled environment, so everything is totally stable temperature. Those things will just sit in free run for that long, and they had to go out by 20 parts per million. So it's still a very, very small variance, and that took 3 whole days. So yeah, don't ever get rid of any conceptions. This can happen. Now, of course, if you're lucky, if you're in a very, very violent thermal environment, like say in the desert, that will happen much, much quicker. But yeah, in a server farm where everything's temperature controlled, yeah, you can go into free run for a long time. Keep an eye on Dante controller. It's one of the big advantages with using Dante VIA, because it will tell you instantly if there's been some kind of synchronization issue. And based upon this experience, you've got 3 days to fix the problem before the boss finds out. So it can be a good thing back the other way, as long as you are monitoring the system. If you see multiple clock masters, what that means is that the devices cannot hear multicast sync messages coming from other devices. So like a lot of network protocols, a PTP master device will send out those sync messages as if it were the master until it hears someone else who has got a better clock, and then it will shut up. If it can't hear that coming in, it will keep saying it's the master. And we pick that up on Dante controller because we use a different communications path to ask the devices if they think they're the master. It helps us to diagnose this. So if you see multiple masters, that means you have a multicast block somewhere, almost certainly. Talking to IT departments, basically take coffee, take wine, take chocolate. They are human, really. We've covered the general overriding principles of how IT networks work with this. We've covered as far as possible terms that are as universal as possible, even though there are some slightly different vendor-specific terminologies. But this is not a replacement for going on a vendor-specific hardware training course. I would certainly go on a Cisco training course if I was using Cisco infrastructure. I'd certainly go and talk to people at HP about their offerings if that's what I was using. So yeah, these are general principles. They're hopefully helpful to go, oh, if this is happening, it may be caused by this, and then somebody with expert knowledge of the infrastructure could go and repair these things for you. Understanding bandwidth requirements is useful. That's universal. Understanding how IP connections are made, so basic switching, basic routing, how sessions are set up is useful stuff. Understanding that QoS is a thing that exists, and also understanding IGMP. One of the things about multicast and IGMP is we have gone into fairly good functional detail about how IGMP works. It's more common now for IT departments to know about it. But one thing I will say, when I first did Cisco certification many years ago, the multicast section was basically, don't use multicast, it's bad, there's no reason for anybody to use it, the end. It's not very helpful. There are still some people of my generation in networks who have that attitude. Luckily, they're dying out. But yeah, just the messaging recently, that anybody who is a current CCNA should have had a more detailed education on multicast. But people of expired certification, shall we say, would have had a different experience. And I count myself, my certification expired ages ago. We had hubs in those days, and serial cables. Do you remember those? So making a network function is about making lots of parts of a jigsaw work together. It's just a big juggling act. There are some nice things about it. Certainly when we're dealing with audio networks, we're generally in our own little corner of the network, so we don't tend to cause harm to anybody else. The risk points are where we're on common infrastructure going towards the core of a network, and that's where the juggling act starts. But typically audio applications present a very, very small core load to a network. It's a very, very edge-centric technology. And we've dealt with the Dante piece of the jigsaw. It's a very, very small part. Anybody who's ever tried to run a mail server or a web server farm will know exactly what a pain doing those things are. Setting up security policies, keeping those maintained is also very, very complex. These are all things that IT guys have to deal with. This is actually relatively simple to do. Presenting this information, that one slide with the magic numbers on it, gets us so far in most conversations. That one slide typically will save 3 weeks conversation. It's quite handy. So next steps. Hopefully the registrations have all gone through to our colleagues in the United States, and if that's happened, they will send you an email with access to the level 3 materials and the exam. So if you go to audinate.com/certify, that will help you get to the materials there. I'm going to hang around to answer any questions people may have. If there's any questions people want to ask publicly, please feel free. Thank you very much for coming along.